All right, so we left off last time talking about how to calculate the resonant frequencies of a sound wave in a closed tube, which has a loudspeaker at one end. And we came up with this fanciful scenario in which we had a tube that was 175 meters long, which works out really nice for the speed of sound because it takes, if you go twice the length of the tube, if you go as a pressure pulse from the loudspeaker to the far end and back, it'll take you 350 meters to do that, or 2 times 175. And it so happens that we're assuming, or just generally taking the speed of sound to be 350 meters per second. So basically it's going to take a sound wave 1 second to do that. You repeat your pressure pulses once every second. You can get a resonant frequency set up in the system. You can produce a standing wave rather than just a traveling wave. And if you do that, repeating every 1 second, your resonant frequency is going to be 1 hertz. That's what it means to have a frequency of 1 hertz, is you're repeating the action once a second. Okay, so we're going to try to generalize from this so we don't have to think about the specifics of this sort of scenario every time when we have longer or shorter tubes, hopefully shorter ones, because these things would be hard to actually construct in reality. So let's start out by introducing a new concept called wavelength. So a standing wave has a wavelength, and to understand it is going to require you to think in terms of sine waves again, or something that looks like sine waves. The standing waves look like sine waves, but instead of thinking in time, how pressure changes over time, we're going to look at how pressure changes in space. So this is for a standing wave, and the wavelength is the distance it takes that standing wave to go from a pressure peak down to a pressure minimum and then back up to another pressure peak. So this is how you can think of it in spatial terms. This is the way I've defined it, going from a peak to a minimum to a peak. It's the same length though, as long as you sort of go through an entire cycle of the sine wave basically, or travel basically the distance it takes to go the length of a cycle in a standing wave, because this isn't changing over time. It's just what the pressure looks like in space at any particular moment in time. So you can go from like the middle of the standing wave down to a trough, to the middle, to the peak again, and back to the middle. So you've incorporated basically the whole cycle in this pattern. That's the same distance as that. Or you can go from a trough to a peak to a trough, same thing. This is a wavelength, and we're going to represent it, hopefully you can see this, we're going to represent it with this Greek letter lambda, which is just how you say L in ancient Greek, or modern Greek too. So that's going to stand for this distance. And I'll just remind you again, the x-axis here represents distance, not time. So it's similar to what we've been thinking about before, but it's going to be different in that one respect. Okay, so that's also why it's called length, right? All right, so the resonant frequencies of a tube are going to be determined by how the length of the tube relates to the wavelength of whatever standing wave you're producing. So in this particular case, we talked about how we're pushing a pressure pulse down the length of the tube, and it bounces and it comes back, then you push again. So sound has to travel down and back again the length of the tube. So the wavelength is 2 times the length of the tube. Or to put it in simpler algebraic notation, lambda equals 2 times L. One way to think about that is to kind of go back to our basic model. So we're pushing at this point, and that's kind of what this peak here in the standing wave is supposed to represent, is a pressure pulse. And what this diagram also shows is that when you have a pressure pulse here, or a pressure peak here, you're going to have a rarefaction at the far end. So if you remember, we walked through the steps of how to generate this thing. You push, the peak goes all the way to this end, and by the time it reaches this end, you have a rarefaction at the opposite end. And then they switch ends, right? So you're winding up with always an antinode on both ends. So if there's a pressure peak here, there's a rarefaction here. If there's a pressure peak here, there's a rarefaction here. And when they kind of switch sides, you wind up with balance in the middle, and that's why we have a node here in the middle. At any rate, you can think about this pattern going from a pressure peak or a compression to a rarefaction on the far end as sort of forming 1/2 of the wavelength of the standing wave, right? We can squeeze 1/2 of this wavelength in here because we're going from a peak to a trough. And if we wanted to extend the whole pattern, we'd have to go up from the trough to a peak, which is the exact same distance as going from a peak to a trough because it's that sine wavy pattern. So it would take us 2 lengths of the tube to go through an entire wavelength in space for this particular standing wave, right? Down and back, then back up again. You can think about it maybe another way, which might be a little easier to wrap your mind around because you can see both of these quantities here. But you can also say that, well, within the length of this tube L, I can squeeze 1/2 of a wavelength, or lambda over 2. So I'm getting from a peak to a trough here, that's 1/2 of a wavelength. And if you just do a little bit of algebra, you can switch this around so that you can see that lambda equals 2 times L. Okay, and that's just for the first resonance of a closed tube. But hopefully that makes sense. If it doesn't, I'd recommend you rewind and review this. Please be kind, rewind. Anyways, because it's going to get more complicated here in a second. All right, so if we want to use this, so if we want to figure out exactly how we can go from length of the tube through wavelength to the resonant frequencies of the tube without having to think so much and just using math to help us, well, let's start out with this basic relationship that distance equals rate times time. That's something you've probably heard somewhere down the line, I hope, but if you haven't, it's good to hear it now because it's true. So we're going to kind of convert these quantities into different entities that we've been talking about already, and we're going to say that distance basically corresponds to wavelength, rate corresponds to the speed of sound, and time corresponds to the period of the wave, how long it takes to go through this cycle. So lambda equals c times p, you can think of it that way. But we also know, we've talked about this at great length in both this class and 341, the period is 1 over frequency. They have an inverse relationship with one another, so we can substitute this for a period here and say that wavelength equals the speed of sound over the resonant frequency. So now we're talking about lambda equals c divided by f, or I'm going to write it out like that. Normally I walk through this on the board so I can take it quite slowly and you can scribble along with me. It might help to scribble along as I'm going through this, but I'm going to try to take it slowly just to make sure we don't miss any steps. But at this point, we kind of just have to work with the algebra. This is the basic relationship. What we want to do is figure out how basically the length of the tube determines the resonant frequency, and we have to kind of work through lambda to get there. So we're going to just flip things around here with algebra. We're going to multiply both sides of this equation by f. That gives us f times lambda equals c. And now for the next step, we're going to divide both sides by lambda. So if you divide this side by lambda, it gets rid of the lambda. You divide the other side by lambda, you get c over lambda. And now we know that frequency is the speed of sound divided by lambda. You can rely on this relationship at all times. This is how it works for resonant frequencies. The one other step we might want to take, though, is substituting something else in here for lambda, namely the length of the tube, and that's a relationship that can change depending on what kind of standing wave you're producing and what length of tube. So if in this previous case we saw that lambda equals 2 times L, so we're going to substitute 2 times L for lambda here, so we're going to say F equals c, the speed of sound, divided by 2 times L. L, we stipulated, is going to be 175 meters because we have ridiculous scenarios to make the math easy, and the speed of sound is 350 meters per second. I'm not writing out units here. It may help you to do that. I'm just trying to kind of make this look a little bit cleaner because they wind up canceling out in the end, basically. So F equals 350 divided by 2 times 175. You can use a calculator to confirm this if you want, but 2 times 175 is 350. So 350 divided by 350 equals 1, and the units will work out to be a hertz. So this is meters per second divided by meters. That gives you basically 1 over second, or cycles per second, which is hertz. So that makes the math even easier for us because we can use this equation to determine what the frequency is going to be based on the length of the tube. Okay, so essentially, if we want to get different resonant frequencies, all we need to do is change the length of the tube. But there's another trick we have up our sleeve, which is that you can set up more than one resonance in a tube, and they will, if you do that, have higher frequencies and shorter wavelengths. And I'll show you why here in a second, and then we'll walk through the implications for the math too. So we've talked about this. I present this example in 341. Again, it might help to review it, or at least I hope it does, because I'm going to review it. Let's say we have a tube here that's closed at the far end, and let's say we have a loudspeaker here. I don't have a loudspeaker graphic, but I'm just going to draw an arrow and say we're going to push a pressure pulse through the tube, and it starts out at time 1. So time is going to be changing as we go down the slide here, going into the future this way. So we have this initial impulse sent down the tube. At time 2, it's going to hit the far end of the tube and then bounce, come back like the tsunami hitting the west coast, and then traveling all the way back to Japan / the loudspeaker, and it comes here, and this is time 3, so the impulse is returned to the other end, and in order to set up this standing wave pattern, we have to reinforce it. So I'm going to push again with a different pressure pulse, and then that's going to combine with this one and go all the way down the length of the tube, and at time 4 we will have reached the far end with this sort of reinforced pressure pulse. The crucial time to think about, or length of time to think about in this scenario, is the time between pressure pulses. So the time between pushes. That is the period of your resonant frequency. How often do you have to push, or how long you go in between pushes is the period. How often do you push is the frequency that we're talking about. And in this particular case, the period is this time minus this time. So it's time 3 minus time 1. We just have to kind of wait one step here in the middle. All right, excuse me. If we think about the second resonance, so this is our basic scenario. We already kind of did the math for this. So we think about the higher resonance, or second resonance is the next one up. We push at time 1 like we did before. And then at time 2, it's going to travel at the same speed because the speed of sound is constant, at least in this model, right, that we're playing around with. So at time 2, that initial impulse is going to hit the end of the tube and come back. And we're not going to wait this time for it to come all the way back before we push again. Instead, we're going to push right at that moment, try to time it so it's right on time with this returning pressure pulse, and we're going to send a new one down the length of the tube. So that by the time that first one comes back at time 3, and we reinforce it here, but that second one is going to be at the far end at this point, because again, these are both traveling down the length of the tube at the same speed. So this will work. We want to be able to be regularly pushing at regular intervals pressure pulses down the length of the tube. So we're going to push time 1, we're going to push at time 2, we're going to push at time 3, and we're going to push at time 4 too, because at that point this reinforced pulse will be at the far end, but that second pulse will be at the loudspeaker end, at the pushing end, and we'll just reinforce that. So we can do this consistently, right? So we're going to push at time 1, push at time 2, push at time 3, push at time 4. We get that standing wave pattern not once but twice because we're reinforcing this guy and we're going to reinforce this guy as well. I kind of stopped here because I don't really know what mixture of green and yellow would look like. Green Bay Packers, I don't know. But you can imagine time 5, it's going to be down here, and then we're going to reinforce this one, which has traveled back here. What is the period going to be for this resonant frequency class? It is going to be the difference in time between pushes. So it's going to be time 2 minus time 1, which is the same thing as time 3 minus time 2, or time 4 minus time 3, so on and so forth. That's got to be consistent throughout. And so if you think about this, just briefly, I'll zip through these slides, hopefully won't take too long. This was time 3 minus time 1 for the first resonant period. And this is time 2 minus time 1 for the period. So this period is going to be half as long as the first period. We're going to wait just half the amount of time, and then once we get to another one of those cycles, we're going to push again at time 3, so on and so forth. So the second period is half the length of the first period. Okay, also, to help you visualize this a little bit, you can think about this in terms of the second resonant frequency. When I have, in the first setup, which is the easiest one to think about, when we have a pressure peak at this end, we have a rarefaction at this end. When the peak's over here, there's a rarefaction down here. And that's going to determine kind of how our standing wave pattern looks. In this case, we are not going to wait. And when there's a pressure peak down here, there's also going to be a pressure peak down here. So the only way this is going to work is if there is a rarefaction or a trough down here in the middle. So our pattern is going to be kind of compressed lengthwise in terms of the wavelength, right? So think about it. We got a pressure peak, we're going down to a trough here, and then we're going back up to another pressure peak at the far end. That's a whole wavelength fitting into the length of the tube, right? And it'll look like this. Here's our bouncing in place standing wave. So we have antinodes at the close and far ends. We actually have an antinode in the middle this time, and we get nodes in between those, kind of at the 1/4 and 3/4 spot in the length of the tube. For our purposes here, though, what we have to worry about is basically this relationship: lambda equals L. The length of the tube is the same thing as the wavelength of the standing wave. You can flip that around and think of it the other way if you want to, if that helps. But hopefully that makes sense, because again, we can kick it up a notch and go to the next resonant frequency higher up. So that pattern, I'm not going to walk you through all the steps conceptually, but it'll look like this. So we're basically squeezing another half wavelength in the tube by doing this. So we wind up pushing at this point when our first pulse is down here, and the timing winds up working out. The wavelength will look like this. So we go from a peak to a trough to a peak to another trough. So we're getting one whole wavelength plus another half wavelength in there. So the length of the tube is 1.5 wavelengths. Or if you do the algebra for that, lambda equals 2L over 3. If L equals 1.5 wavelengths, then the wavelength is 2/3 of the length of the tube. So from here to here is 2/3 of the length of the tube, basically. Okay, any guesses on what the relationship between lambda and L will be for the next highest resonance? It's actually pretty easy when you see the pattern. Hopefully you've seen it already, but if you haven't, I'll remind you without going back to the previous slide that for our very first resonance, lambda equaled 2L, and I'll kind of give you a hint here. In this case, if lambda equals L, you can rewrite that as lambda equals 2L over 2. And then for the third one, it's lambda equals 2L over 3. So we're going from the first resonance, lambda equals 2L. Second resonance, lambda equals 2L over 2. The third resonance, lambda equals 2L over 3, so on and so forth. For the fourth one, hopefully you can see it's lambda equals 2L over 4. Or you can simplify that a little bit and say lambda equals 1/2 the length of the tube. In each case, we're going to kind of squeeze the wavelength a little bit, make it a little bit shorter so it fits in this tube, and we still get a resonant frequency. Okay, so what are the implications of this? For that second resonance, if lambda equals L, we can do the math again. Here's our kind of default relationship between frequency, speed of sound, and wavelength. We can substitute L for lambda in this case. If we go back to the 175 meter tube, we find out that if we fill in the appropriate values here, 350 meters per second for the speed of sound, 175 meters for the length of the tube, then the frequency of that resonant frequency for the second resonance in that case is going to be 2 hertz. You get 2 repetitions per second when you do that. That's just 350 over 175. If you do it this way, this probably won't be too much of a surprise when we get to the answer. Again, we're going to start out with this guy. We're going to substitute this quantity for it. So 2L over 3 gets substituted for lambda. If you do a little bit of math for that, it turns out that F equals 3C over 2L. And otherwise, we just got to substitute the correct values here for C and L, 350 and then 175 for L. So that's 3 times 350 divided by 2 times 175. We'll simplify this a little bit. 2 times 175 is 350. And normally, again, I write this on the board so you can take it at the right speed, but this 350 together will cancel out that 350. And basically it'll tell you that F is 3 hertz. So hopefully you're seeing the pattern. For the first resonant frequency is 1 hertz, second resonant frequency is 2 hertz, third resonant frequency is 3 hertz. I'm not going to do the math again, but if you did the math the right way at least, and calculate it for the fourth resonant frequency, it would be 4 hertz, right? It would just keep going up like that, step by step. That's ultimately winds up being no more complicated than counting, so I'm going to assume nobody has a problem with that, but you can walk through the slides again if you want to make sure you understand it. Here's the pattern, at least the way we can write it in sort of the most general form. So the first resonant frequency is C based on this equation C over 2L, where we substitute 2L for lambda. That winds up being 1 hertz. Second resonant frequency, we substitute L for lambda. We get 2 hertz for the frequency. In the third case, we get 2L over 3 for lambda, and that winds up giving us a resonant frequency of 3 hertz. You can keep going and going and going, and then you can write this in its general form as N. So for resonance N, where that's just basically your resonant number or your formant number, then that value for that frequency is going to be N times C over 2L. And I'll just pause here again. This quantity, when you're dealing with the same tube in every case and just looking at all of its different resonant frequencies, C over 2L is not going to change, but N will change when you go up kind of the number of formants, right? So N is 1 for the first formant, 2 for the second formant, 3 for the third formant, so on and so forth. So those formants should have a clear relationship between each other. They're kind of going to go up each time by the value of C over 2L. In this case, that is just 1 hertz. So it's simple. Okay, that's how it works in the closed tube case. And we walked through that first. It's like a baby grammar in syntax because it makes it a little bit easier to understand. The actual system we're dealing with is more complicated than that because our tubes, which has the loudspeaker down here and the end up here at our lips, our tubes are normally open when we're speaking. We normally open our mouths when we say something, it turns out. And so when we do that, we have to think about the acoustics in a slightly different way. So speech doesn't involve closed tubes, and instead we're going to think of the articulatory tract, the vocal tract, as a tube with one open end here, and then our loudspeaker pulse source at the closed end in the vibrating glottis. It's giving us these complex waves we talked about at length in looking at voice quality and EGG waveforms and all that stuff. So at what frequencies will this tube resonate? In order to figure that out, we have to kind of draw the standing waves a little bit differently in the length of the tube. So the trick you have to remember to kind of flip this around a little bit is that when a pressure pulse hits an open end of a tube, it doesn't get reflected back in the same way that like throwing a tennis ball against a wall will just bounce it back to you. Instead, you get an anti-bounce. It anti-reflects, which is weird, and it's not easy to kind of wrap your head around that. But when a pressure pulse goes out the open end of the tube, a rarefaction comes back. And when a rarefaction goes out, a pressure pulse comes back in. One way to think about that, which helps me at any rate, is you can think about like a wave coming into the shore at the beach. So it's a pressure peak of a wave, right, from the ocean. And then it pushes all the way in. And if you stand in that one spot when like on the edge of the beach, when like the wave crashes by you and rolls past your legs, you can feel what comes back is not another wave. It doesn't bounce back, right? What comes back is the undertow, and you kind of feel like you're being sucked out a little bit as the wave goes the other way. And then the whole cycle repeats, which is fun, which is one reason why people like the beach, I guess. But yeah, so you get the opposite pattern kind of going in and out at that point. So that's what happens at the open end of a tube when we're speaking, when we push sound out the open end of a tube rather than a closed tube. The way this is going to look is, say, we have our loudspeaker end here. Here's our glottis. We're going to push a pressure pulse down the length of the tube. It's going to travel all this way. And when it gets to the end, that pulse is going to dissipate out into the world, and a rarefaction will come in behind it. And weirdly, that rarefaction is going to travel back down the length of the tube, bounce, at this end because it's effectively closed. That rarefaction will come out the other way, and when it goes through the open end of the tube, another pulse comes in, and you have to wait until that pulse reaches the original closed end where you're pushing before you push again. And I don't unfortunately have that extra step here, but that would be basically step number 9 here in this sequence. So you have to wait a little longer. You have to wait for this rarefaction to kind of do its entire cycle, and before the initial or a version of the pressure pulse will come back to you so you can reinforce it. What that means for the way we've been drawing these things is that in open tubes, you're always going to have a pressure node at the open end of the tube. You can't build up pressure there consistently or let it get sucked out effectively either. So it winds up kind of being at balance with like the outside world is one way to think about it. At the far end, though, you will get these sort of true bounces for pressure peaks and pressure rarefactions. So we get an antinode at the glottis end, and then we get a node at the open end. And if you think about it, the pattern that's going to form, this being the entire length of the tube from the glottis to the lips, we're only going to be able to squeeze 1/4 of the wavelength in there because we're just going from an antinode to a node. We need to keep going down to another antinode to another node, and I'm going to run out of space really quickly, and then finally up to another antinode again. It's going to look a little bit easier in this representation, but I'm still going to run out of room. So this is the first resonance in an open tube scenario. So I'm going from an antinode to a node at the far end. Then I have to go down to another antinode. That's another length of a tube, because that's also 1/4 of the wavelength. Then another length of the tube to get back up to a node. Then another length of a tube to get up to another antinode. It's going to take me 4 lengths of a tube to complete the entire wavelength in standing wave terms. So lambda is going to equal 4L. If it's easier for you to think about it the other way, and maybe it is because you can see it, but L is going to be 1/4 of the wavelength, or L equals lambda over 4. And again, algebraically, these two equations are equivalent to each other, right? You just have to flip them around. The pattern you get for the second resonance is similar in that you have this antinode at the loudspeaker or glottis end, and then you have this node at the open or lips end. And what's getting added on here is another loop kind of in the middle. So you go down from an antinode to a node to an antinode, and you get back up to a node. You're not quite getting all the way through the whole wavelength of the standing wave. You still have to go up one more link here, or 1/4 of the wavelength. So that means that you're able to get in 3/4 of the wavelength in a single length of the tube, or L equals 3 lambda over 4. If you flip that around, that means that lambda equals 4L over 3. So basically 4/3 of the length of the tube is the length of the wavelength. We'll keep going for the next resonance. Still antinode here, still a node here. We're just adding another loop here in the middle. And if hopefully you can see, this is an entire wavelength of the standing wave for once. And then we're adding on 1/4 wavelength at the tail end here. So in that case, L equals 5 lambda over 4. Or if you flip that around, then lambda equals 4L over 5. Or basically from here to here is like 80% of the tube, or 4/5 of the tube. Okay, been walking through that a little bit quickly, but want to repeat it so you can kind of understand the pattern. Hopefully it's not going to be too much of a surprise if I tell you that, well, actually I'll let you kind of work it out. You can pause the video here because normally I ask this question in class. But what would the value of lambda be for the next resonant frequency? What would the standing wave look like, first of all, and then how would that translate in terms of this relationship between lambda and L? For now, I will just say, hopefully you can start to see this pattern, right? So in this first resonant frequency case, we have lambda equals 4L. In the second resonant frequency, we have lambda equals 4L over 3. In the third, we have lambda equals 4L over 5. This 4L part is staying consistent throughout. And maybe it'll help you to imagine that the first one, you divide 4L by 1. Second, you divide it by 3. Third, you divide it by 5. So this denominator, or the bottom part of the fraction here, is just going up by the odd numbers. So 4L over 1, 4L over 3, 4L over 5. hopefully you figured this out on your own, but the next one will be 4L over 7, right? How do we characterize that mathematically? If we want to make a more general formula, we can write it out like this. So the wavelength of resonance n, or lambda sub n, equals 4L divided by 2n minus 1. So this 4L part of this is staying constant for all of these. And this is just the bit that enables you to kind of jump up by odd numbers in the denominator of the fraction. So if you think about it, for your first resonance, n equals 1. So 2 times 1 is 2, minus 1 is 1, right? So 4L over 1 for that one. If you're working with the second resonance 2, then n equals 2. 2 times 2 is 4. Minus 1 is 3. And you get 4L over 3, so on and so forth. This quantity will just jump up every other number for every increase in n. We can also use this relationship to kind of go back and determine how frequency, or figure out how frequency is determined by the length of the tube. So our basic equation is F equals C over lambda. We're going to substitute all this for lambda in the bottom of this equation. And we get F sub n, the nth formant frequency, or nth resonant frequency, is C divided by 4L over 2n minus 1. It's a bit awkward to have a fraction in the denominator of a fraction, so we're going to flip this guy so that 2n minus 1 appears in the numerator, and just write it out like this. So F sub n equals 2n minus 1 times C over 4L. And this will tell us what the specific resonant or formant frequencies are for an open tube. All we have to know to figure out the answer to this is what the speed of sound is, and we have a basic assumption for that. We need to know the length of the tube, and then we have to also know what formant frequency we're talking about, which n, basically, which resonance. Okay, so we're going to play around with this. We're going to put it into action, and we're going to make a prediction, because that's what we do in science. Otherwise, the game is just not fun, or maybe doesn't even have a point. So let's say that the articulatory tract we're dealing with is an open tube of length 17.5 centimeters, which is about 7 inches long. And you might already notice that I'm picking kind of a convenient number here, but trust me, this is actually kind of realistic. So what's the first resonant frequency? The first resonant frequency means I'm going to substitute 1 for that value n. That's all it means. And for L, I'm going to substitute this length, 17.5 centimeters. For C, I'm going to substitute 350 meters per second. So there's two different ways you can do this. If you want to think in meters, you can say, well, C is 350 meters per second. But then you also have to convert this measure into meters. 17.5 centimeters, it turns out, is 0.175 meters. So when you do that math, it winds up looking like this. N is 1, so 2 times 1 minus 1 is 1. Times 350 just gives you 350 at the top. The bottom is 4 times the length of the tube, so 4 times 0.175. If you want, you can work that out with a calculator. 4 times 0.175 is 0.7. You might be more comfortable working this out with a calculator. 350 divided by 0.7, it turns out is 500. So the first resonant frequency here is 500 hertz. If it's easier for you, you can do this in terms of centimeters. And in that case, the speed of sound, instead of being 350 meters per second, is 35,000 meters per second. So you just multiply this entity by 100, right? This is part of what makes the metric system nice and easy to use. And in that case, you'd have 17.5 for this quantity. So 4 times 17.5 is 70. Maybe it's easier for you to divide 35,000 by 70. My guess is that most of you will probably use a calculator to figure that out anyways. So maybe don't worry about it, but just so you know. And this is the point where I say that it's okay to use a calculator to do these problems, because most people don't want to do them in their heads. And that includes on the final and midterm exams, although I'm not entirely sure at the moment how we're going to structure those. So sit tight with that. But if you need to use a calculator, use a calculator. You might also want to use a calculator to derive the second resonant frequency. The only thing that's going to change here in this equation is what n is equal to. So here we're going to have n equal 2. So you can think this is 2 times 2 minus 1, this whole quantity winds up being 3, right? If you do the math, well, before we walk through the math, you can kind of think about it. For the first resonant frequency, it was basically, this wound up being 1, and this C over 4L ratio wound up being 500 hertz. And the only thing we're changing here is this part. So basically we're saying we'll take 500 hertz and multiply it by 3. And that might be something you don't need a calculator for, because 3 times 500 is 1500, right? You can walk through it the other way if you want to, if that makes you feel more certain about this. But basically this becomes 2, so this whole quantity is 3. 3 times 350 is something like 1050. 4 times 0.175 is still 0.7. If you use a calculator again, 1050 over 0.7 is going to wind up being 1500 hertz. But there's going to be a pattern here, basically. The next resonances are all going to go up by odd numbered multiples of the lowest resonance. The first one is 500, the second is 1500, the third is 2500, then 3500, so on and so forth. Just like what we saw a second ago, maybe, because of this relationship, because this is going up by odd numbers in the bottom of this ratio, or these fractions, the resonant frequencies will go up by odd numbered multiples of the first one. You can count on that. And that works for a nice kind of clean open tube with no interesting perturbations or other deformations in it, basically. And I can show you that it works conveniently when I speak. So this is me saying, I don't know if you find that inspiring or not, but maybe this will be more exciting. I've turned on the formant tractor here so we can kind of see these a little bit. Maybe I'll turn that off. What I'm going to do is kind of try to click on the middle of the first formant frequency in the middle of the vowel. What do I get? It says 518. That's pretty close to 500. What if I click on the middle of the second one? It's almost 1500, 1478. What does this one say? This one is about 2500 or so. Okay, it's hard to click on the exact value there, but basically I'll show you what Prot says. This is using the formant listing again. So Prot says 500 for the first one, 15, 37 for the second, 26, 86, so on and so forth. It's going up basically 500, 1500, 2500, because it turns out the length of my vocal tract somehow conveniently is 17.5 centimeters or thereabouts. Almost as if somebody out there wanted me to be a phonetician, because I didn't control that. But be that as it may, this is how it works. This is how you get the resonant frequencies of an open tube. It's how you get the resonant frequencies of your vocal tract. If you produce a vowel like schwa, which is basically opening up your mouth and phonating and letting the chips fall where they may, you get these specific resonant frequencies, which are based essentially solely on the length of your vocal tract tube. I'm a fairly tall guy. My morphology tends to be on the longer side of things, so your vocal tract might be a bit shorter. We're going to actually do an exercise where you produce a vowel like this and measure your formant frequencies and try to figure out what your vocal tract length is using this math. But just so you know, though, that relationship should work the same way. So your second formant frequency should be 3 times the first formant frequency. The third formant frequency should be 5 times the first formant frequency, so on and so forth. They should be evenly spaced all the way up the scale. And what's going on in the big picture is that the fundamental frequency of a speech sound is a complex periodic wave. We talked about that at length when we were talking about what's going on at your larynx when you voice things. So that gives you a series of harmonics. A complex wave consists of a series of harmonics. They are all at frequencies at integer multiples of that fundamental frequency. They will pour into your vocal tract from the glottis. Those harmonics which match the resonant frequencies of your vocal tract will be amplified. Those which do not will be damped and will lose intensity. And these resonant frequencies of the vocal tract are simply determined by the length of the vocal tract in the most basic case. The resonant frequencies of a particular articulatory configuration are called formants. We've seen them before, and the way we've seen them is because when we produce different formant frequency patterns, we get different vowels. There's a correlation there. And we're going to talk more about how we get those different formant frequencies in the next series of lectures. But for now, we've gotten to schwa through basic physics alone. So I hope that all makes sense. This is kind of a tricky one because there's a fair amount of math involved. And we're going to use this math again. We're going to recycle it in a couple of lectures. So if you don't understand it, please go back and make sure you know how to walk through it from the ground up. But otherwise, I'm not going to say anything more about this. So we'll see you next time.